So topic is alternating current. Now suppose we have this resistor R. It is connected with a current which is changing its polarity. The instant at which the current is flowing in this direction, we will calculate the power which is, suppose this positive direction, positive I square R, so the output power is I square R. When the current is flowing in this direction for the next half cycle, this is negative, then the power is minus I square R, so we will get the same power. I square R, I square R. It means the power output from any resistor does not depend on the polarity of the current, whether it's going in this direction or in this direction, because both are squared and the output is delivered by the resistor. Now, alternating current and the alternating voltage both are sinusoidal and both are in phase to each other. So this cycle is positive, this cycle is negative, this value is called peak value, and this is the peak value in opposite polarity. Similar graph for the voltage, because the voltage and current both are directly proportional and in phase. Now again, we take two identical resistors, this resistor R and this resistor is also R. This is connected with alternating voltage supply, alternating current supply, and its potential is suppose 100 volt here. The voltmeter is reading 100 volt. When a joule meter is placed near this resistor, suppose it is receiving 10 joules per second, mean the energy is dissipated from this resistor at the rate of 10 joules per second. Now this identical resistor is connected with a DC supply, direct voltage, direct current supply, and it is variable. Now the joules meter is placed near this identical resistor and the voltage is adjusted until energy is delivered at the rate of 10 joules per second. Similar to this, once the energy rate is same, we will determine the voltage of the DC, and this will be approximately 71 volt. Look, in alternating 100 volt job through the same resistor is exactly equal to 71 volt direct voltage through the same resistor. Mean same energy is dissipated from the same resistors by the two supplies, but one at 100 volt and other at the 70 volt. So this is alternating and this is direct. So this is the difference. Now, it means this direct voltage is more efficient than alternating. What's the reason behind this alternating voltage, alternating current? It keeps on changing the direction. So when it has to change the direction, the charged particle, the charge carrier, retards to rest and then changes the direction. So during retardation, during changing the polarity, it loses the energy as heat. But in the case of this current, direct current, there is no change of the polarity. It's going straight. So there is no such loss of the energy. So this is the difference between alternating current and the direct current. So for the loss of the energy, this alternating supply requires more voltage, and this direct voltage or direct supply requires less voltage to deliver the same power from the same resistor. Now, practically, this resistor is working at the 71 volt because the energy is delivered at the same rate as delivered by the DC. So this supplied volt 100 is the peak voltage, and this is actually working voltage, actually required voltage. This is called RMS voltage. So the RMS voltage of any alternating peak voltage is equal to that direct voltage which delivers same power from the same resistor. This is the definition. So we will write VRMS of any alternating voltage, the peak voltage, is equal to that direct voltage which delivers same energy at the same rate from the same resistor as delivered by alternating voltage or alternating current. So the relation between these two, VRMS is V naught, the peak voltage supply divided by under root 2. Now both voltage and current are directly proportional to each other. Similarly, the RMS current of any alternating current is equal to that direct current which delivers same power from the same resistor as delivered by alternating current. Now same formula, current RMS is equal to peak current divided by under root 2. Suppose we have alternating voltage. This is the voltage. This is peak voltage, and the 71% of the peak voltage is RMS. Similarly here, this is the minus V naught, and this is the RMS voltage. We cannot calculate the average of the voltage. Reason, because this is positive, this is negative. Suppose plus 5 plus minus 5 divided by 2, it becomes 0. So instead of the average, because the average becomes 0, we calculate the RMS, which is actually the working voltage. Similarly, if this is the current against time graph, So this is the peak current, and this value is the RMS current. So RMS current is I naught divided by under root 2. We can't calculate the average current in the AC because it becomes plus I plus minus I divided by 2. So the answer is 0. So instead of the average, we use RMS, which is 71% of the peak current, because 1 over under root 2 is 0.707. So approximately 71%. These formulas are only applicable when there's a sine wave, but in the electronics, the output is not a sine wave, it's a square wave. So in the case of the square wave, this peak power, this peak, sorry, voltage is exactly equal to RMS. So we can't apply formula. This I RMS is equal to I naught by 2 or V naught over under 2 RMS for the square waves. So these I naught over under root 2, V naught are only applicable when the voltage and current in the sine wave form. For the square wave form, the RMS value is exactly equal to the peak value. Now, the power from the AC, power is a scalar physical quantity. So the power at the y-axis, time at the x-axis. So due to the alternating current, the power across the resistor is also fluctuating. This is the peak power. So the peak power is equal to product of peak current and the peak voltage. But the actual power, which is the RMS, is the product of RMS multiplied by voltage RMS. So this is the power which is supplied to the appliance, and this is the power which is dissipated from the appliance. I mean, this is the input and this is output. Now, this RMS power can also be written as in the sine waveform for the alternating current, for the alternating voltage, I naught divided by under root 2, V naught divided by under root 2. So the power RMS is equal to then I naught V naught under root 2 into under root 2. It becomes just 2. So we can write then RMS power is peak power divided by 2, mean the 50% of the peak power. So when we have to draw the line for the RMS, so at the middle of this graph, we will draw the line. So this is representing the RMS power. Similarly, we can compare the power from the DC and power from the AC. So this is the resistor. First, it's working at direct current, which is I. So this power from the direct current will be just I square R, because there is no change of the polarity, no loss. But when the same resistor is supplied with the alternating current of the same magnitude, so the working current here will be not the supplied current, it will be RMS. So the power from the alternating current will be IRMS square times R. Now the power AC is equal to I naught divided by under root 2 square times R. And this I naught is I. So we can write power from the alternating current I square R divided by 2. Hence, the relation is the power out from the alternating current is the power out from the direct current divided by 2, mean the power of the direct current 2 times the power of the alternating current. So current alternating is changing direction according to its frequency. If the frequency is 50 hertz, mean in 1 second 50 times there is a change of polarity and there is a huge loss of the energy. So due to the loss of energy, this power of the AC is smaller than the power of DC. How much? 50 times. There's no change of the polarity of the direct current. That's why the direct current power, DC power, is double of the AC power. Yes, the power of the DC is double than AC, but the problem with the DC is it cannot be transmitted from one station to the other station. Reason, transformer works on the principle of mutual electromagnetic induction, and which requires varying magnetic flux linkage. But the direct current cannot provide varying magnetic flux. Its flux is constant. So direct voltage cannot be stepped up or down. Mean we can't alter the voltage in magnitude, not high to low, not low to high. So the transformer does not work for the direct voltage because transformer requires varying magnetic flux and it cannot be provided by the direct current, direct voltage. We can convert alternating current into direct current. But to remember, alternating current will be at the high voltage, but the direct current is used at the low voltage, 6 volt, 12 volt. So before changing the alternating current into direct current, we will use step down transformer. So first, high voltage alternating current is converted into low voltage current. Suppose this is the high voltage alternating supply. It is connected with a transformer. This is the symbol for the transformer, and this is step down transformer. So this is the primary coil, this is the secondary coil. Number of turns of the secondary coil is less than the number of the primary. So this is a step down transformer. And then after converting high alternating voltage into low, it is converted into the direct, and this is called rectification. So the conversion of alternating current into direct current is called rectification, and the diode is used for this purpose. So the diode is used as a rectifier. We have done half-wave rectification in O-level. For example, this is the low voltage alternating current supply. A diode is connected in series and then suppose a lamp is connected with it. So when CRO is connected between these two terminals, this is the wave trace on the CRO. This is alternating. When this A side becomes positive, then B will be negative. For this instant, this is positive side, this is negative side. When the positive side of the battery connected with the positive of the diode, negative side of the supply connected with the negative side, this is forward biased, mean it allows current to pass through it. So it becomes conducting forward bias. So current flows through it and the bulb goes on. When CRO is connected across the lamp, we can get this voltage. Suppose this one. But for the next instant, due to alternating supply, this side becomes negative, this side becomes positive. So when negative of the battery is connected with the positive side of the diode, this is reverse bias. It stops the current, no conduction. When the current is blocked, bulb will remain off for this cycle, so no output shown by the CRO, but when it again becomes positive, we will get another ripple, then no output, then this positive. So this is the two-way current, and this is just one wave current. So this is two-way alternating current, and this is half wave, one side direct current, but this is called the half wave rectification because it is coming at intervals. This output is at interval, the regular interval of time. So here is no voltage, but this is one side, so half wave rectification. But in A level, we have to study full wave rectification. For example, this is a power supply alternating. First, we will connect it with the transformer, step down transformer. This is the primary coil, and then this is the secondary coil. These two are the terminals, output terminals of the transformer, and low voltage across AB. Then these terminals are connected with two diodes, one connected with A and other connected with the B side, and then both are connected with a common resistor for the output, and this is the earth source. So A and B are at alternating voltage, low alternating voltage. Suppose this is the polarity, this is the voltage. When this side becomes positive, this will be negative. This is diode number 1. This is diode number 2. For the A positive, this diode 1 is forward bias. Diode 2 is the reverse bias. So this D1 will allow current. This side is at the 0. So the A at the high potential, and this is the earth potential, low potential. So the current flows from the high potential to the low potential. So current will flow in this direction and then through the resistor. So this is the direction of the current through the resistor. So we can get this one. So here is the current across the resistor. But when polarity changes, B becomes positive, A becomes negative. Now D2 is forward biased and D1 is reverse biased. B positive high potential and this earth low potential, then the current flows from high potential through this diode D2, and again current is flowing down, is going down. It means for the next interval, the direction of the current same. Look, this is full wave rectification. For both cycles, positive, negative, the current through the resistor in one direction. So alternating current is converted into direct current. Now, this voltage has a problem. First one is it fluctuates between these two values. It is continuously fluctuating, so it's not a working voltage. And number two, this rectifier requires earth connection, which is also not workable. So for the rectification, this terminal is earth terminal, so it's not workable. So it's not practical. So we will change the circuit, and instead of this rectifier, we will use bridge rectifier. So the new one is bridge rectifier. Okay, in bridge rectifier, same first transformer. Suppose this is the supply for the transformer, is alternating low voltage. Then we have this circuit. First diode connected in this direction. Second diode suppose in this way. Then third diode in this direction. Suppose this is the P terminal. One forward bias, other reverse bias. And then these two diodes opposite sides but same dimension. These two diodes opposite sides but same dimension. Now one wire connected with the P and the other wire is connected here. Suppose this is the Q. And then these two terminals, suppose these are A and B, connect a resistor between A and B. So this is called the bridge rectifier circuit. Suppose this diode is D1, this diode is D2, this is D3, this is D4. Now when this P side becomes positive and this Q becomes negative for one of the cycle, then this D1 is the forward bias and D2 is the reverse bias. So the current flows through this diode D1 towards this B. So the terminal B becomes positive. For the positive B, this D4 is the reverse bias. So the current flows through the resistor in this direction. When the current reaches here, this A becomes positive. Now for positive A, both diodes D2 and D3 both are forward biased, but the current will flow towards the low potential. This is positive and this is negative. So this is the direction of the current after the A. Now the direction of the current across the resistor, suppose like this. Now when this Q becomes positive and this P becomes negative, then positive Q, this is the forward biased, this is reverse bias. Now the current is going in this direction through D4. When it reaches at B, again B becomes positive. So this is now reverse bias. So again current goes towards resistor in the same direction. When it reaches at A becomes positive. For the positive A, D2, D3 both are forward biased, but the current will go to the negative potential, low potential instead of Q, the current will go towards this P because this is negative at this instant. So circuit is completed. So the current in the resistor is again in the same direction, and we will get full wave rectification, no gap, and without any earth connection. So this is the full wave rectification without any earthing, but this was the full rectification with earth connection. So this earth connection through bridge rectifier is removed. But the other problem is still there. The voltage is fluctuating between 0 and the maximum value. And we have to decrease this fluctuation. And the decrease in the fluctuation of the voltage, decrease in the fluctuation of the current, right, is called smoothing. Smoothing of ripples. And this smoothing of the ripple is done with the help of capacitor, which is connected parallel to the resistor. Okay, now a resistor, this is the resistor, but a capacitor is connected parallel to this resistor. So for smoothing of the ripple, capacitor is used. It's connected parallel to the resistor. What is the purpose of this capacitor? Okay, when the voltage increases to this level, which is extra voltage from the resistor, then this extra voltage is used by the capacitor to charge itself. But when the voltage from the supply decreases, the capacitor discharges itself and delivers its voltage across the resistor. When again the voltage from the supply becomes greater than the required voltage by the resistor, so capacitor charges, then discharges, charges, discharges, and look, the voltage is not coming to the zero level, because when the voltage from the supply drops, voltage stored by the capacitor is delivered to make it higher than the zero level. Look, the discharging of the capacitor is exponential. So this is not a straight line, it's a curve. Now for this time, for this gap, there is a charging of the capacitor. And for this time, this gap, next one, there's a discharging of the capacitor. Now do remember, charging occurs between capacitor and the supply, and the discharging between resistance and capacitor. And we have done that discharging times directly proportional to approximately this resistance when capacitance is constant. So due to resistance, charge flows through it slowly. So the capacitor takes longer time to discharge itself instead of the charging, because there's a less resistance between supply and the capacitor. So it charges quickly due to the large current. When this process continues, charging and discharges, the final shape of the voltage is this. Look, there is a less fluctuation between the maximum and the minimum value. So here, instead of fluctuation between peak and zero, so there is a fluctuation between these two voltage, which is smaller than the previous one. When we have to take the voltage output for any working, we will use this average value, not the RMS value, because this is one side voltage. This is only positive. We can take the average. For example, this is 10 volt and this is suppose 8 volt. Then the proper working voltage will be the average 9 volt. So for the numericals, we will not use the 10 volt, not use the 8 volt. We will use this working average volt, which is the middle of 10 and 8 volt. Now suppose the capacitance of this capacitance increases, either replace the capacitor or connect another capacitor parallel to this capacitor to increase the capacitance. When the capacitance increases, resistance constant, discharging time increases, then this line will be like this. This line will be like this. So when capacitance increases, larger capacitor is used. So there is more smoothing in the ripples. So the height of the ripple will decrease due to the decrease in the height of the ripple. Look, the average value will also increase. For example, first it was 10 and 8, but now it is between 10 and 9. When it was 10 volt and 8 volt, the average was 9. But suppose now this is 10 volt and this is 9 volt. Due to more smoothing, then the average will be 9.5 volt. So by connecting a bigger capacitor, larger value of the capacitor, larger capacitance, by using larger capacitance, number one, the height, the ripple decreases, more smoothing, and the average output voltage also increases, but we cannot make it 100% straight line because it is rectified from the alternating voltage. So this is the chapter, alternating current.